I'm talking about you, but oh,
There we go. There we go. All right.
Why did you say that?
All right, everybody, let's get started. Just a heads up, you might have remembered, or you might remember I mentioned on Wednesday that I was getting over a sinus infection. I'm not really getting over it, or at least not yet. So my voice is a little rough, but it'll be all good. So, but if my voice starts cracking and whatnot throughout lecture today, well, that's why. Okay, I am giving you a homework today. It is not due on Monday. It is due on Wednesday. Okay? The reason why is because today what I want to do is I want to discuss deflection. Okay? I will go ahead and tell you that our lecture today is going to be a little different. It's going to be a little bit more like movie time. We're not really going to do any in-class examples today because I want to set the stage for how we compute deflections and structures. And we're going to primarily use energy-based methods in the class or the method of virtual work. So I kind of want to explain what those are before we start using them. So today, the purpose of the lecture is to just sort of take a step and make sure that it makes sense. Because, you know, I would say that what we've been doing that right now, or up till now, has been pretty straightforward applications of statics. And then today's going to be different, okay? So because it's different, I'd rather take a bit and sort of, you know, discuss that on its side, let the knowledge seep in, then we'll use it on Monday, okay? Any questions? So again, no homework due Monday. I promise that's not a trick because it's Friday the 13th. The homework is due on Wednesday, okay? Sound good? All right, everybody get the code. Okay. Okay, so today what we're going to do is we're going to discuss deflections. This is our first foray into deflections, and we're going to periodically discuss deflections throughout the semester. Excuse me. Is this going to work? Hold on. Let's try this again. Usually I can click the pen. There we go. There we go. Okay. All right. So up until now, I would say that the main flavor of our class has been painted on forces. In other words, like up until now, we've been focused on results of an analysis that are related to forces, like reactions, internal forces in truss members, etc. But what I want to recognize is that when you apply loads to a system, the system deforms. Okay? And I want to discuss that, those deformations. When we do statics, we assume rigid body behavior, but that's not the case in the real world. In the real world, structures exhibit some deformation, either a translation or a rotation. Okay? I want to discuss that because there are really two reasons why. First off, just deformations are important from a design standpoint. We typically have, when we design beams and columns and bridges and buildings and what have you, we typically have deformation limits. In other words, if we look at the, bless you, if we look at the floor beams in a building like this, not only must they be strong enough to not fall down and kill people, but they must be stiff enough to not deflect too much. And sometimes the deflection limits are what actually govern which members we select. So that's one reason. Another reason is purely for analysis. Up until now, we have been analyzing structures that are determinate. Okay? In other words, I equals 0 for every structure that we've analyzed so far. What if I does not equal 0? What if we have an indeterminate system? How do you analyze an indeterminate structure? Well, the way that you analyze an indeterminate structure is understanding the relationship between how much force you apply and how much deformation that you get. So you have to understand that in order to be able to even do it and be able to even model it. So that's really the two reasons why we're interested in that in here. Okay? So I want to look at this truss. Okay? to be clear, I'm not asking you today to do any of these calculations. I'm going to walk you through them together, okay? And to be clear, we've looked at this truss before in here, okay? Now, a couple things. Here's the truss, and our goal in the discussion is going to be to determine the vertical deflection at B, okay? And so what I mean by that is the following, okay? I got myself, let's see if my animation's still working. Oh, it's still working, yay. So I prepared a quick analytical model of this structure, and by the way, you all are going to know how to do this by the time the semester is over. This is an analytical model of that truss, okay? Now, you can notice sort of a pink and blue frame that's sort of animating, okay? What I am proposing is that the pink frame represents the structure that in its undeformed shape before we apply the loads. And then the blue frame is what's happening as you apply those loads. And the structure deforms, right? Sort of like a rubber band, okay? Like you apply load, it deforms, okay? So to be clear, every joint that's not restrained by a boundary condition experiences some deformation. Like for example, this joint 1 right here, that's where the pin support is, it's not moving at all. But this joint is moving, it's actually moving left to right and up and down. This joint right here, it's only moving left to right because it's got a roller right there. Does that make sense? Okay? So every joint is experiencing a deformation. But for the purposes of our discussion today, I'm going to be interested just in this deformation, the vertical deformation up and down right here. Okay? That's just for our discussion purposes. Does that make sense? When you analyze this with software, it gives you the deflections everywhere. But by hand, we're going to be looking at deflections one at a time. Okay, so far so good? All right. Excuse me. Okay, so we're going to discuss this looking at the vertical deflection right here. I want to look at this truss, and does anybody notice anything different about this truss as opposed to the problems that we've done so far? We have the area of each member. So imagine I took each member and I said samurai sword or lightsaber. I guess the simplest way of saying it is quote unquote, how big around is it? Okay? In other words, these horizontal members are a little bit beefier than the diagonal members. Everybody see that? So I'm giving you that information that I didn't give you that. I didn't give you that before. Okay? That didn't matter. And for a statically determinate structure, it does not matter, okay? Statically determinate structures will give you the same response whether they're made out of steel or concrete or popsicle sticks or what have you, except for deflections. The deformations will be different. Now, not only am I giving you how big around, quote unquote, or how beefy each of these members are, but I'm also going to tell you what material they're made out of, okay? So I'm going to tell you that these truss members are made out of aluminum, okay? And from a mathematical standpoint, the material itself doesn't really matter. What matters is this number, okay? E, the Young's modulus. Y'all remember this from 216? Like if you, how many of you are in CE 321? Dr. Noss materials class. So you all are going to do tensile tests, I think probably a little later this semester, where you will do stress strain tests and actually determine these experimentally for different materials. This is a material characteristic. A material characteristic means that aluminum has an E value. Concrete can have E values. Brass, steel, so on and so forth. Okay? So we have to, when we determine deflections, we have to fully characterize the structure. And what I mean by that is not only must we characterize the geometry fully, but we must characterize the constitutive properties fully. So like if we look at this member, let's look at member AB. I know that members AB, or member AB, I know that it's 12 feet long, but now I know it's 12 feet long and its area is 4 square inches. So I now fully understand the 3D properties of that member because volume is area times length, right? And then now applying a material to that, I fully understand what's going on. Okay, everybody with me so far? Now, I'm going to go into some wild theory ideas. I know I'm in a room with a bunch of engineers. And I know that at the end of the day, sometimes the engineers are like, Dr. Mike, just tell us how to do it. Am I right? I understand that, okay? So this slide, what I'm going to do is tell you how to compute deflections and trusses, okay? We're going to use the method of virtual work, okay? And there's 3 steps. I'm going to show you these 3 steps, and then I'm going to show you why we do what we do, okay? So I'm going to handle that first, because I know some of you are like, come on, just tell us what to do, okay? I'm going to do that first, okay? So the first thing that you need to do is you need to analyze the truss, okay? Fully analyze the truss under its applied load. So every member, we have a reported tension or compression, okay? That's step 1. Everybody should be okay with that at this point, right? Okay. Now I'm throwing some terminology at you. I'm calling this a real analysis, okay? I'm using that term because I'm saying that we are analyzing the structure when it's subjected to its actual real loads, what's really on the structure, okay? So we analyze the structure and get this. And by the way, we've done this problem before, right? We did this problem a while back. This was our first truss example. So far so good? Okay. We then need to perform a second analysis. And that second analysis, we call it a virtual analysis. Now here's how the virtual analysis works. We kick off every one of the original real loads on the structure. So we take this 15 kips, this 20 kips, 10 kips, take them off. Gone. This is Sparta. Okay? Kick them off. And we replace it with a single load. Now that single load has a magnitude of 1. You can think of it like a 1 kip load or a 1 kilonewton load. Really it's just a load of 1. Okay? Now, we place that load here. Why are we placing it at joint B? Because that's what we're interested in. If you remember, our goal in this example is to determine the vertical deflection at B, okay? So for this example, I'm putting the load at B, okay? I am placing the load in a vertical orientation because I'm interested in finding vertical deflection. If I was interested in finding horizontal deflection, I put the load going horizontal, okay? Now not only is the load vertical, but it is downward, okay? So I could have taken this load and placed it upwards, okay? But I put it downwards, okay? I put it downwards because I, as the analyst, am making an assumption that at the end of the day, joint B will deflect downwards. And by the way, that is a correct assumption, right? Because here's joint B before the load, after the load, it goes down, right? Make sense? So we do a real analysis, we do a virtual analysis, and then we plug and chug. Okay, and what do we plug and chug? We sum up what I'm going to call the energy components of each of the members. Okay, now the energy components are really easy to compute. So what that means is that for every member in the truss, I compute this term right here. It is little f times big F times L divided by EA. Okay, EA is the E and the area for each of the members. L is the length. Okay, but what about little f and big F? Little f is each of these virtual forces, and big F is each of these real forces. Okay? Does that make sense? Because of the nature of this calculation, it is a very tabular friendly calculation. So nudge, nudge, wink, wink, what software program do you think would be very nice for doing truss analyses in this fashion? Excel. Excel. This is a very Excel friendly calculation. Okay? So like I said, you're going to sum this up. So when you sum this up at the very bottom, we get a positive number, and that positive number is 0.237. So what that means is, because it's positive, our assumption is correct, and the deflection is 0.237 inches downward. And that's it, okay? So I'm going to go into why this works here in a second. Like I said, it's going to be a little while. But before we go down the rabbit hole of why we do what we do, does everybody kind of just understand the nuts and bolts of doing this? Okay, and don't worry, we're going to walk through this in more detail. So far, so good? All right. So let's introduce energy methods, okay? Energy methods might seem a little scary. It's really not, okay? Let's go back to basic physics, okay? Basic physics says that energy cannot be created or destroyed, right? All we can do is take energy and convert it into different forms. Everybody in here has done an energy-based physics problem at some point in their academic career. I'll give you an example. Here's a Goomba, right? So we got the Goomba. The Goomba is here on top of this platform, right? While the Goomba is on top of the platform, the Goomba has a stored gravitational potential energy of mgh, right? And then the Goomba walks off the platform. And what does the Goomba do? Starts to fall, right? And then what happens? That gravitational stored energy, that gravitational potential energy, is converted into kinetic energy. And we can calculate the kinetic energy as 1/2 mv squared, right? So we can set the two energy components equal to one another and determine, what is the speed at a given height, right? This is how you determine that independent of air resistance, objects fall at the same rate because it's independent of their mass, right? Remember this from physics? This is an energy method, okay? The idea is that you just set the energy terms equal to one another, okay? Now, this is not a kinematic course. We're not dealing with structures that are flying across Third Avenue, okay? We're dealing with structures that are sitting still, but we're dealing with structures that also deform, okay? So I think that Mario Brothers is the wrong video game to analogize what's going on with structures. I think we should take a look at Link, okay? So let's take a look at Link here, all right? So, anybody know what I'm talking about? Okay, good. So we got some folks of culture. There we go. Breath of the Wild. Okay. I haven't really played the most recent one, so it's a shame. Yeah. All right. Here's Link drawing a bow. Okay. So I want you to picture in your head a rubber band. Okay. Now take that rubber band, stick it between your fingers. Okay. So here's the rubber band, stick it between your fingers. Okay. Now here's the rubber band in its neutral state. Okay. Now, let's say that I want to shoot a wadded up thing of paper at Mr. Stroh. Okay? So what I'm going to do is I'm going to face Mr. Stroh. I'm going to take the rubber band. What am I going to do? I'm going to yank it back and let it go. Right? Okay? So let's talk about a couple of physical observations. Okay? Would you agree that the amount of energy is proportional to the amount or to the length that I yank back that rubber band? Right? If I do this, it might go a little bit. But if I yank on it and let it go, it's going to go a lot further. Does that make sense? So the more energy that I store in the system, the more energy I will get as a result. Okay? So far so good? Okay. Now I want you to think, now the second thing I want you to do is I want you to think of drawing the bow as two separate actions. Okay? I want you to think of it as two events. Okay? The first event is external work. Okay? And what I mean by external work is here's the rubber band, I deform the rubber band. Okay? How do you define work in physics? What is it? Force times distance? Right? So if you have a force that moves through a given distance, work is done. Right? And the product of that is the work at a given point. Is everybody okay with that? Now, that is the first event that happens. The second event that happens is that the rubber band stores energy. I mean, if you have the rubber band in your hand, okay, imagine that I said, okay, here's the rubber band. I want you to yank on it, and I want you to just hold it there for 3 hours. That's going to get kind of hard, right? Why? Okay? Because the rubber band has deformed, it has responded by absorbing that energy, right? Does that make sense? It's absorbed that energy. The more external work that you do to the rubber band, the tighter the rubber band is. Same thing with Link. The more that Link draws the bow, the more energy is transferred to the arrow. Does that make sense? I propose that those two terms are equal to one another. Okay? I propose that external work done and stored energy are the same thing. So instead what I'm going to do is I'm going to throw some terms at you. I'm going to throw external work done. I'm going to use the letter W. I'm going to do stored strain energy. I'm going to use the letter U. Okay? So to get a little bit more detail, the external work done is going to be the product of forces and distances and moments and rotations. Okay? Now, there's a little bit of details that I'm leaving out right here. because total work done, we're going to do some integration, but suffice it to say that's kind of what's going on. Now the stored strain energy, if we're bringing it back to mechanics, to engineering 216, 213, and CE 312, we're going to look at stored energy from axial forces, stored energy from bending moments, stored energy from shears, stored energy from torsion, and so on and so forth. And I propose that they have to equal one another. Okay? Does that make sense? Now, there's a couple of assumptions that I'm making here. For example, one of the assumptions that I'm making is that there is no vibration. If I wanted to include kinetic energy, I can look at vibrating structures. And you would kind of need to do that if you were looking at earthquakes, for example. You would have to account for the fact that as an earthquake hits the building moves. So there's a kinetic effect as well. So you got to throw another term in there. So the math gets a little trickier whenever you have vibration thrown into the mix. But we don't have to worry about that in here. Now, a couple things. We're going to do linear elastic behavior in here. That's what we're going to do. Most structural analyses assume that behavior. Some don't. And there are some specific applications where you actually perform a nonlinear analysis. They're usually very specific, and in practice we try and make it as straightforward as possible. But that's more of a design problem than it is an analysis problem, like moment redistribution or direct analysis for steel frames and things like that. We can also consider other forms of structural response like torsion, thermo, shear, so on and so forth. Some of these we're going to look at. In a lot of applications, we can neglect them. So for example, in trusses, all we're going to care about is the energy from the axial load. Okay? Is everybody with me so far? Okay. All right. Let's look at external work done. Okay? Now I've got one load applied here. Don't get too worked up about that because I'm going to have two loads later. But for now, let's just keep it simple. Okay? So I have the rubber band. I apply a load, and it stretches some amount delta. Okay? Would you agree that if I doubled that load, I would double the delta? Everybody okay with that? So you could chart the comparison between delta and the load like this. Everybody okay with that? Like, as the load increases, the deflection increases. If the load was 0, the deflection was 0. Everybody okay with that? Now, at some given point, you could do P times delta, but I'm more interested in the total amount of work done. And the total amount of work done would be all this, the area under the curve. So we're going to integrate, but I'm sort of trying to avoid the integrals wherever possible. Remember, we're doing linear elastic behavior, so that's a triangle. So 1/2 P times delta would be the total amount of work done on a given bar, or on a given rubber band, or so on and so forth. Okay. All right. So far, so good. Okay. That's the external work done. Now remember, when link draws the bow stores energy. So how does the bow store energy? How does that work? Okay. Let's go back to 216. Do you remember that? Sigma equals F over A, that there is a stress. How about that? You remember Hooke's law, that there is a relationship between stress and strain, and the relationship between stress and strain is defined by Young's modulus, or the elastic modulus, and that is a material-specific parameter. What about strain? Isn't that the change in length over the original length? Y'all remember that? So, if I plug into this equation right here, I can say, well, instead of sigma, let's put F over A. Instead of strain, put delta over L, and solve and get that. Y'all remember that from mechanics? That should be a pretty familiar problem. And so I can write the stored energy kind of like this. I can say that as we store some internal energy, we respond by deforming FL over EA. So I can calculate the stored energy as F squared L over 2EA, because it's just 1/2 base times height. Okay? Is everybody with me so far? Now, some of you are probably thinking, Dr. Mike, why are you using different letters? Like, why is it P before, but it's F now? Well, why are you doing that? Why are you using different notation? Okay, for a single bar, it's obvious that they're the same. I mean, if I have a bar and I yank on it with some axial force P, it responds with some internal force F, they're the same. Everybody okay with that? That is not the case in a truss, okay? If I have a truss that has 30 members on it and I put a 20 kip load, this member might see 30 kips in tension, that member might see 40 kips in compression, that member might see 0. So there is a difference between the applied forces, the external forces that you put on the system, and the resulting internal forces that the members experience. Does that make sense? So that's why I'm saying there's a different notation, okay? Everybody okay with that? So, all right, so let's walk through this, okay? So if the external work has got to equal the stored energy, okay? So what I can do is say the external work is 1/2 P delta, the internal energy is F squared L over 2EA. So just solve for delta. And I can do the same thing for a system of members. I can say that the external work is 1/2 P delta, and for a truss, instead of a single U-term, I'm going to get a bunch of U-terms because the truss is going to have, what, 5, 6, 7, 12 members, however many members are in the truss. So I'm just going to have a U-term for every one of the truss members, just sum them up, right? And that summed energy has got to equal the external work done. Set these two equal to one another, solve for delta, right? If I'm interested in finding the deformation, that should be pretty easy. Sounds good, right? All right? Everybody with me so far? So this all sounds very pleasant. This all sounds very easy to follow, okay? But I'm going to throw a wrinkle into the problem. But before I throw that wrinkle, I want to make sure that what I'm talking about so far makes sense. Everybody okay with that? Okay. Now, I want to talk about this sentence because this sentence is really important, okay? I propose that the internal stored energy has got to equal the external work done. But if I want to find the deflection, I have to have a load where that deflection is. 1/2 P times delta, okay? The problem with this whole enterprise is this. Actually, let me go back a slide. This is the problem. I propose that the stored energy inside this system has got to equal the external work done. But if I want to solve for a deflection, which load do I use? Do I use this load? Do I use this load? Do I use this load? Do I use a combination? How does that work? I mean, I think everybody would agree that if I had just the bare truss and I put 20 kips right here, it's going to drag B down, right? Everybody agree with that? But let's assume for the sake of discussion that I had the bare truss and all that was on the truss is this 10 kip load. Isn't that going to push B down too? By how much? What about this? Is this going to have an effect? They all are going to have an effect, right? The problem is this. The way I have formulated this, the problem that with the way I formulated this is that this formulation is good, great, grand, and wonderful as long as I have a structure that only has one force on it. Like Link drawing the bow, the only external load is Link pulling the bow at one point. But in the real world, that's not the case with trusses. In the real world, there's loads all over the place, right? So how do we handle that? How do we get around the fact that a structure has multiple loads at given locations? Okay, that's the issue that we need to resolve. The issue is with this definition of W. You can only solve for the deflection where the load is applied. And in real structures, that's difficult to isolate. So what we're going to do is we're going to put a load there. In other words, if I'm interested in finding the deflection at B, the way I'm going to handle that is I'm going to put a load at B, okay? So the way that we'll do that is we will preload the structure. So the first thing that we will do is apply the structure with this sort of preload, this fake load, which I'm going to call a virtual load, and then we will put the full load on the system. Okay? So let's go back to this. Let's go back to our bar example. What happens if we put 2 loads on the bar? Okay? So let's take a look at this. So here's my bar. I'm going to put 2 loads on the bar. Okay? The first load is going to be P1. I propose that if you put P1 on the bar, it's going to respond by stretching some amount delta 1. Okay? Then what I will do is put on top of that P2. Okay? If I put P2 on top of that, it then responds by stretching an additional amount, delta 2, right? So phase 1 is putting this on, phase 2 is adding this on top of it. Okay? So after phase 2, that's the total load, that's the total deflection. Okay? Does that make sense? Everybody with me on that? And again, I knew this is the part where I say it's getting a little wild. Okay? Now remember, our ultimate goal is delta 2. Okay? Because like I said, what I'm going to do is I'm going to preload the structure with P1, but the real forces on the structure are P2. In other words, I really don't care about this delta 1. This delta 1 doesn't matter to me. Okay? Because delta 1 is the deflection under this load, and this load's fake. It doesn't exist, right? But I'm putting on there to make the math easy. Okay? I'm going to put P1, it's going to stretch some amount. Then I'm going to put this on top of it and get this. My ultimate goal is to solve for that. Everybody with me on that? I know that's a little weird, so let me take a second and see if that conceptually kind of makes sense. Let's walk through what happens. So the first thing that I do is I put this fake load on there, and I get some amount of stretch, delta 1. Then what I do is I stick the real loads on top of it. I stick the real loads on top of it, and now I've got this. So this is sort of the same idea. I've just got more terms, and so I'm going to call it W1, W2, and W3. And all I'm doing here is just a little bit of algebra. Okay? Oh, sorry, didn't mean to go for it. So the total amount of external work done is this part plus this part plus this part. Notice how I've got a half and a half, but no 1/2 here. Why no 1/2 there? Because that's a rectangle. Yeah, there's no triangular component there. Does everybody kind of see what's going on? So the idea is I've got my system. I'm going to put this fake load on it, and then the real load's on it. And so as a result, I get these 3 energy components. So far, so good? So what happens? So this is the external work done. What happens internally? Internally, the system stores energy. It stores this fake amount of internal force and then a real amount of internal force. So internally, I get sort of the same idea. I'm not expecting you all to go through all this algebra. I just want you to kind of get the idea. Does that make sense? All right. How are we doing so far with the ideas? How are we doing so far? Okay, so is this okay? This is the external work done. This is the stored internal energy. Okay? Now I propose W has still got to equal U, right? Like, here's my bow. Okay? If I take my bow, I pull it a little bit, and then I pull it a lot, I'm storing a little bit of energy, and then a lot of energy, but it's still the same amount of external work and the same amount of stored energy. Everybody okay with that? That's still true. Okay? All I've done here is broke it up into these 3 terms. Okay? Now, engineers are clever, and here's where the cleverness arises. W's got to equal U, but what's really interesting, is that each of these components are equal as well. Like this one equals that, this one equals that, this one equals that. And I'm an engineer, so I'm lazy, so I'm going to use the ones that I think are the most useful. So I'm going to look at the W2, okay? So I propose that this term has got to equal that. So let's really dig into that a little bit. What is that saying? So this is saying P1 delta 2 equals this. Okay, so what is this over here? How do we get that stuff there on the right? Well, what do we need in order to compute this? We need the length of the member, we need the E, we need the area. Those are easy. We also need the little f and the big F. What are the little f and the big F's? The result from the virtual load, the result from the real load. Remember how I told you that we're going to sum up these terms for all the trusses to compute deflection? That's where it comes from. Now I propose that has got to equal the external work done. Look at this term. What is this? This is P1 times delta 2. What is delta 2? Delta 2 is what we're after. That is the deflection due to the real forces on the structure. That's what we care about. But what is P1? P1 is that fake marker load that we put on the system to make the math easier. We, as the engineer, can choose whatever value of P1 that we would like. Okay? So look at this equation. If I wanted to solve for delta 2, and I could pick whatever value of P1 that I would like, what would you pick? 1. Does that make sense? That is the method of virtual work. Okay? So, from here on out, the presentation is a lot more straightforward. Okay? I know that that was a little, and there was a lot of out there ideas, but from here on out, it gets really, really simple. Okay? This is the basis of the method of virtual work. The method of virtual work is an energy-based method to compute the deflections in structures. Just so you are aware, if you open up your textbook will be broken up into 2 broad classes of how to compute deflections. You're going to see listed energy methods, and you're going to see listed geometric methods. Okay? Geometric methods are very specific applications for very specific types of problems, mainly beams and frames. But energy methods will work for any problem, any load, anywhere. Okay? So that's why I focus on energy principles, because it works across the board for any problem. And it's really easy to follow. Okay? So the method of virtual work, sometimes it's called the unit load method. It's an energy-based approach to compute deflections. Okay? We're going to start by applying truss deflections, because that's what we're doing right now, is trusses. But later on, we're going to look at beams and frames. Okay? So, and we're going to use the same approach, just a little bit different application, because beams and frames have different mechanics. So we're going to have to do a little bit of integration, but the integrals are really, really easy. Okay? All right. There are other applicable methods to solve for deflections, but I think that the method of virtual work is the one that's easiest to remember, and it is the most universally applicable. This is what I focus on in here. Okay. So let's go back to our example. Let's go through how we would actually compute the deflections. Okay? So here's the structure. What's step 1? Solve the truss. Okay? So you actually need to solve the truss, but these numbers should be familiar, right? We've done this before. Okay? We've done this problem before. So you fully solve the truss, you get the forces in every member. Why do we need the forces in every member? Because we need to sum up the energy in the whole system, right? So we need the compression and tension in every single member of the truss. So the force in this member, this member, this member, this member, this member. Those are the real forces, and I'm going to call this capital F. So capital F, I'm going to use for the real forces. And that's a little bit different notation than your textbook. Your textbook uses F and then F sub V. I use big F and little f. So just so everybody's aware. Then we apply the virtual load. This is this P1. Okay? Now how does this work? We kick all the loads off, and then we only put the unit load. Okay? The reason why we're able to do that is because, remember, we preloaded it. We put the little load, or the fake load, then we put the real loads. But when we looked at our energy, all we had was a little f and a big F. So we're able to separate the analyses. So what we do is we say, all right, let's kick all the loads off the structure and put a single unit load. Where do we put that load? We put it at B. Why do we put it at B? Because that's where we're interested in calculating deflections. Why do we put it vertically? Because we're interested in a vertical direction. Why do we put it down? Because we're assuming it deflects downwards. If we get a negative answer, so what? It acts upwards. So far, so good? Solve the truss. So you got to solve it again. So one of the downsides of problems like this is you do have to solve the structure twice. Not really any way around it. It is what it is. But usually we can exploit symmetry. Okay? For example, this truss is entirely symmetrical. So we have this member equals that one, this one equals that one, this one equals that one. So if you have symmetry, you can probably make the problem a lot easier. Keep in mind you're also kicking off all those real loads and only putting on this fake one. So chances are there might be zero force members here that weren't there before. So you can make the analysis a lot faster. Okay, you see why we talked about that before? Because, and you're going to see that on our in-class example, when we look at the virtual analysis, there's going to be a lot of zero force members that we can just identify really quickly. So far, so good? Okay, so now we have the method of virtual work. So when it's all said and done, we analyze the truss. We have two sets of analysis. We have the real loads, which are usually measured in kips if we're dealing with US units, and then little f, which doesn't have any units. Remember, this, you can think of it as one kip, but really it's just one. So this 0.625, it's not 0.625 kips, it's just 0.625. Then what do? Plug it into this. So what do we need? We need an E value. E value is in kips per square inch. We need an area. An area is in square inches, okay? So we also need the member length. What unit should we use to describe the length of each member? Inches, right? Because kips per square inch, inches squared, inches. You need to describe the member length in inches so that everything cancels. So whenever you set up your tabular computations, make sure that the member lengths are in inches, okay? Then what you do, like I said, very Excel friendly. Stick the little f's and the big F's in the problem. Make sure that, so typically when I do the computations, I assume tensile forces are positive. So because it's tabular, anytime there's a negative value, that's compression. You can actually assume compression positive and get the same answer. You just need to be consistent. And customarily, we assume tensile forces are positive. And then what do? Sum up the energy. Little f, big F, L over EA. So bam, 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 divided by this is that. This times this times this, divided by that is this. This times this times this, divided by that is this. Just do it in a row, sum it up. And when it's all said and done, we got a positive answer, the deflection's downward. So let me take a step back. Again, I told you, it's a little bit of a wild lecture. Any questions on this idea? You weren't expecting this, were you, today? This was different. So this is why I want this to seep in. Monday we're going to do a problem, okay? Right now, I'm giving you a homework in case you want to get started on it, but it's not due till Wednesday, okay? Yes?
How does the math change if you wanted to calculate like the horizontal deflection?
We're going to look at that on Monday. And all you do, just put a horizontal load and solve again.
Okay.
Yeah. We're going to look at that on Monday. Because we're gonna, if we have time, we're gonna do the vertical deflection and the horizontal deflection. Sound good? All right, I'm gonna pull the code up one more time. I will see you all next week.